back for another round. This is Mr. Doolin. I thank you for tuning in. What we're going to do today is we're going to take a look at strong versus weak in terms of acids and bases. And so let's jump right into it. A strong acid or base, and my A/B, that's a definition or abbreviation for acid and base or base. All right. So strong acids and bases, they dissociate completely. And so by completely, we mean in all intents and purposes 100%. Now, does everything go to 100%? No, not in reality. But for our calculations to simplify everything, we're going to assume that they dissociate 100%. And so what that means is that every possible hydrogen ion is going to be released, or every single hydroxide ion is going to be released. All right? Okay. The opposite of that is actually a weak acid or base, and essentially they're just the opposites. They don't dissociate completely. Now, the one thing that we do want to make sure that we understand right off the bat with our weak acids and bases, since they don't dissociate completely, they will reach an equilibrium. Yeah, right? Everybody's right now, I heard the moan, I heard it. So what we have here, these are our Ka and our Kb values, right? This is my dissociation constant for acids, my dissociation constant for bases, all right? So when we're dealing with weak acids and bases, we're going to have Ka and Kb values, all right? Strong acids and bases, we will not get that information. Okay, so what strong acids do I need to know? Your common strong acids are hydrochloric acid, HCl, hydrobromic acid, which is HBr, and hydroiodic acid, which is HI. We also have sulfuric acid, which is H2SO4. We have perchloric acid, which is HClO4, and then we also have nitric acid, which is HNO3. And these are my 6 common strong acids. These are the only ones that you're going to have to be familiar with. All right? And the question is, well, Mr. Doolin, how do I know if it's a strong acid? If it's one of these 6, it's strong. If it's not, it's weak. All right? Okay. Now, the other end of the spectrum there is what are my common strong bases. And so common strong bases are your group 1 metal hydroxide. So that would be like your sodium hydroxide, right? Your group 2 hydroxides, which would be like your magnesium hydroxide. Notice I'm writing my formulas correctly there. And then also you would have group 1 and group 2 oxides. Now, what does an oxide look like? That's like your sodium oxide or your magnesium oxide. So those are my strong bases that I need to be familiar with. Notice it's a little bit more general because I'm just giving you group 1, group 2, and either pair it up with hydroxide or with oxygen itself. And again, same rule applies. If it's not strong, it is weak. All right, and so now let's take a look at some of the dissociation reactions of our strong acids and our strong bases. So I'll look at hydrochloric acid first. So to write the dissociation reaction, I'm just going to actually just split off a hydrogen and leave behind a negative ion. Very, very simple. Don't overthink this, right? We've actually just got one hydrogen by definition of Bronsted-Lowry. We donate a hydrogen, right? So it releases one of its hydrogens. If I was going to graphically show you what this thing looked like before dissociation, this being 100%, right? And then versus after dissociation, what we would end up with is all of my ions or all of my original molecule completely dissociated. So notice over here, this is before and this is after dissociation. Notice in the after, I've got none of the HCl molecules still left. So that's very important that you visually see that and you get it in your head that a strong acid, strong base completely dissociate. The same would be true for like NaOH. If it was going to dissociate, it would give me Na plus OH minus. And 100% of it would dissociate. The graph would look very, very similar. All right? Okay, now what if it's not strong? Like here you go. Oh, I did want to show you a sodium oxide, one of the metal oxides. When it reacts with water, so I put sodium oxide in water, what I'm going to end up with is sodium hydroxide. And that balances out that way. And that's why those metal oxides are actually very basic. It's because they produce a hydroxide, a metal hydroxide, when they enter into water, and then this will actually dissociate into Na plus and OH minus. So the metal hydroxides, you have to, or the metal oxides, I'm sorry, you have to watch and understand that every time a metal oxide is put in water, it's going to give me a metal hydroxide. There you go. So a metal oxide will give me a metal hydroxide, which will then dissociate into its respective ions, okay? All right, now the next one that I'm going to show you, and I won't tell you, it's HC2H3O2. That's acetic acid. And so I want you to tell me, what's the dissociation reaction look like for acetic acid? Does it dissociate completely? Well, hopefully you can look at your list there and say, well, it's not one of the strong ones. Well, that's right, it's not. So therefore it is weak. And so the dissociation will actually reach an equilibrium because I'm going to have some of this acetic acid left over. I will have some hydrogen ions in solution, and I will have some of the acetate ions in solution as well. So if I was going to visually represent this in the before and after, right? Before dissociation, we've got HC2H3O2, all of it. And then after dissociation, I've still got a lot of the original acid molecule present, and I don't want to draw it that big because I don't have very much of the ions themselves. All right, and so it's real important to understand here that this is my before and this is my after dissociation. And notice I don't get a whole lot of products produced. And then also I want you to notice I drew an equilibrium arrow here. So since this is an acid, I would actually expect to be given a Ka value here. And my Ka would actually be equal to the concentration. Let me change colors here. Concentration of H plus times the concentration of C2H3O2 minus over the concentration of HC2H3O2. Notice, in this one, I keep the reactant in there because this is actually considered to be an aqueous substance, okay? All right, so there we go, ladies and gentlemen. And the other thing I do want to point out before we stop is the stronger the acid or base, the weaker its conjugate. So think about that for a second. The stronger the acid or base, the weaker its conjugate. So if I'm looking at this particular situation and I ask myself, well, I'm looking at Cl minus versus, let's say, the acetate, and I want to know, hey, both of these, if this is my acid, this is my conjugate base, right? If this is my acid, this is my conjugate base. So both of them are considered to be bases, so which one would be a stronger base, right? Well, think about your equilibrium, right? My equilibrium does not go very far in that direction, so the reverse is actually more favored than the forward in terms of what my K values are going to be. And by the way, these Ka values are all going to be less than 1. They're all going to be less than 1. If it was greater than 1, I would get a significant amount of products there, right? And so generally speaking, again, I'm going to make this statement, and it's something that you've got to get in your head. The stronger the acid or base, the weaker its conjugate is. And that's a statement that will help you so much on down the road if you can actually get your head around that idea right now, okay? All right, if you have any questions, ladies and gentlemen, get them down. I'll see you in tutorials for those. Otherwise, I will see you in class.